Welcome to Pomodoro Joe for Saturday, July 22nd, 2023. Today we're doing LeetCode problem 688, Knight Probability in Chessboard. This is a medium problem. So, we're given an n by n chessboard. The knight starts at the cell defined by row and column, and attempts to make exactly k moves. So we're given k, row, column, and n. All right. The rows and columns are 0 indexed, so the top left cell is 0, 0, and the bottom right cell is n-1, n-1. A chess knight has 8 possible moves it can make, as illustrated below. Each move is 2 cells in a cardinal direction, and then 1 cell in an orthogonal direction. So that's 2 cells up, and then 1 cell left or right, or 2 cells down, and 1 cell left or right, or 2 cells left, 1 cell up or down, and 2 cells right, 1 cell up or down. Okay, each time a knight is to move, it chooses one of 8 possible moves uniformly at random, even if the piece would go off the board, and it moves there. The knight continues to move until it has made exactly k moves, or has moved off the chessboard. Return the probability that the knight has remained on the board after it has stopped moving. All right, and then we have some examples, and our probability will be some fraction. All right. Cool, let's put 25 minutes on the Pomodoro timer and we will get started. So for this one, my first thought is the depth first search. Basically, you stack up all the possible places it could go, keep track of the number of moves it's made, so you'll have some like row, column, and k or remaining k. So keep track of all the possible locations, how many moves it's made, then you put those on the stack, and then you just keep processing the stack until you run out of spaces. Count how many spaces are still on the board, divide that by the total number of spaces you could have moved to, that's your probability. However, that will be inefficient. I can already see, so for example, if I move 2 up and 1 to the right on my first move, then I can move 2 down and 1 to the left on my second move, end up where I started, and just keep going in circles. And each one of those circles will actually be processed every single time. It won't take advantage of any type of caching or dynamic programming. So that leads me to think I might want to do some dynamic programming for this. So let's start with that. Let's have some dynamic programming here. So we'll have a DP, and that will just equal, let's see, we'll need basically the entire board. We'll have n by n, and then we'll want to keep track of our different moves. So essentially we will move, and in order to do that move, calculate the probability, we can look back at our last move, figure out what was the probability of that move at this same square. So here's the idea. You figure out where you're going to move to, what square you'll end up on. Then you can just update the probability on that square. So you keep updating the probability you'll end up on that square for every move that you make. Then at the end, you can just add up all the probabilities of the squares that are still on the board. All right, so let's do that. We'll have some representation of our board. There is 0 probability that you start on this spot, and that's going to be times n. And that's for every whatever, doesn't matter, in range n. So that's going to give us 2 dimensions. So this gives us our columns, and this gives us our rows. So this gives us our board. But we want to keep track of the board for every possible move. So we actually need to have this entire board replicated for every whatever in range, and we'll have to do k. All right. And actually we need to have k moves, so k plus 1. Okay. And then we do need to kick off our entire thing. So we have to have our start. So our DP at our start location. So that's move 0. And let's see. Actually, let's make a note of what these are. This is move, column, or we can do row, column, it doesn't matter. Row and then column. All right, so this is what our DP represents. So for our DP on move 0 at this row and this column, we have a 100% chance of being on that spot. All right, And now we just have to go through every move. So for I, and actually I'll call it move. For move in range k plus 1, because we have k moves. All right. Let's see. Oh, we're going to be looking back. Well, let's keep going and we'll come back to this in a second. We might have to redo that. So for every row in range n, and for every column in range n, we'll just go through every square on the board. We have some row and column. All right. Now we need to add some delta to get our move. All right, so let's keep track of our deltas here. Let's do this. We'll have a move delta. This will just be an array. And let's see, what are our possible moves? Well, we can go left by 2 and then up or down. All right, so we're doing row and then column, so I guess it doesn't really matter. Technically, going left by 2 here and then up or down, we'd have +1 or -1 first, and then our -2 second. But it doesn't really matter. Let's just do this. So we'll move 2 in one direction, and then either -1 or +1. So that's one option. Another option is we move -2 in one direction, and then -1. Let's line these up. Or we move +2 and then -1. Actually, let's line these up here too. All right. Next, we will move either 1 or -1. So let's start with -1 in this direction. And we can do -2. Or we move +1 and -2. Or we move, let's see, +1. Let's get these lined up again. And -2. Oh wait, I've already got that. Hang on. Let's get this straight here. 2, -1, 2, +1. -2, -1, -2, +1. All right, so we have 2, 2, -2, -2. Then we have -1, -2. Let's do another -1. Or let's follow our example up here. Let's do positives first. So +1, then -2, +1, and +2. Then we'll do -1 and -2. And then let's see, this will be a -1 and a +2. So does this cover everything? Let's see. Let's just go through it. Why not? Okay, so technically I'm doing row and then column, but I don't think it really matters. We just have, let's call it 2 and then -1. All right, that covers this one. And then 2 and +1, that covers this one. Then we have -2 and -1. And then we have -2 and +1. All right. Then we've got flipping our direction, -2 and +1. And then let's see, +2 and +1. And then -2 and -1. And then it should be +2 and -1. Yep. Okay. So we've covered all of our directions. Next, we actually have to add those to our current row and column. So for every delta in our move deltas, so we'll have some previous, where did we come from? Because I'm going to be looking back to find the probability that we came from some location. It's a little bit confusing, but this is how it's going to work. So our previous column, that's just going to be our current column. Let's see. Let's do row first, why not? And we're going back, so we can do minus. I guess it doesn't really matter since they're symmetric. Okay, so this is the move that we're trying to make. Now let's check to see if we are still on the board. All right, so if our previous R if we were not on the board, so that's less than 0, okay, that's one way we can be off the board. Or, all right, I don't need these. So if we were off the board on the bottom, or the previous r is greater than n, or greater than or equal to n, or the previous c is less than 0, or the previous c is greater than or equal to n. So these are all off the board. We either less than 0 or greater than our bounds. So if any of those are the case, we'll just continue. We were out of bounds. We weren't going to come from that square anyway. Otherwise, we came from some square, this previous row and column. Well, then let's look at that. Well, then we need to check the probability that we were actually on that square. So the probability that we'll end up on this current row column is the probability that we were on that square. And then we also have to divide by 8 because there were 8 different possibilities. So let's start out with just what was the probability we came from this square, this previous r and c. So then our current dp for this current move, for this row and this column, so for this move ending up on this row and this column, we increase that probability by the probability that we were on this previous row and column and the previous move. So we have to look at the dp for the previous move. And then we look at the previous row and the previous column. All right, so now we've added up all of these probabilities, but in the end, after this for loop, after this internal for loop out here, we need to take our probability here and divide it by 8 because there were 8 different possible moves. And so the probability is divided among those 8 probable moves. I'll just put it that way. And it's a floating point divide because we want this to be a floating point value. All right. Now that we've got this, we'll go through, add up all these moves. So in the end, we should have some checkerboard or some chessboard here that's filled up with all these different probabilities. And what's the total probability that will end up on the board? Well, it's just the sum of all the probabilities of every square. So let's have some result. Set it equal to 0. And then just for every row in our dp, actually we have to go dp on this move. So this will be dp at k. We'll just sum that dp. So we'll sum the values in this row. And at the end, we'll return our result. All right, so I think this should do it. So we have some dynamic programming. It's basically an empty chessboard to start with. It's going to be rows, columns, and we have a stack of these empty chessboards, one for every possible move. So we have rows, columns, and then up to range. Oh, so this is something we didn't address. I meant to come back to this. So we're going through all of these stacks of, you can think of this as stacks of chessboard. It's like 3-dimensional chess. We're making these moves. When we're going back from this second move, I guess, or we're even on the first move, we're looking at our previous move. Well, the thing is we don't have a previous move if we start at 0, so we actually have to start at 1. And that's why we go from 1 to k plus 1. So that's going to cover all of our moves. All right, so we've got our empty chessboard. We are going to start at this row and column, 100% probability. So this is our move 0. All right. Then we have all of our deltas. I think I covered this. We did check them, but we'll find out soon if we got it wrong. Then for every move, we're going to start at move 1. We're going to check every row and column, just go through our entire chessboard, take a look back. Where were we coming from? Or where are the different possible moves or squares that we came from? So we look at all the previous possible rows and columns that we came from to get to that square. If it's out of bounds, we couldn't have come from that square because it says right here, if you go out of bounds, you stop moving. So if we have some previous square that was out of bounds, we can just continue. We ignore that. If it was in bounds, then we can check what was the probability that we were actually on that square. Then we can add that probability to our current square's probability for this move. At the end of all that, we do have to divide our current probability by 8, just because you have 8 different possible moves for every single square. So every time you have this new probability, like these additions actually get divided by 8 because you only have 1/8 the chance of this probability getting transferred to this square, if that makes sense. Okay, and then at the very end, we'll just go through and add up all the probabilities of the squares in the board. That's our chance of staying on the board at the end. Okay, let's run this, see how we do. And we don't pass. Let's see, we're pretty close. I wonder if I got one of my moves wrong. Let's double check ours here. We've got positive to positive 2. That actually looks right. All right, what else do we miss? Looks right to me. Oh, here's the problem. We need to accumulate all the rows. I was just resetting. That was a silly mistake. Let's try that one more time. All right, let's see if this works. Okay, and we pass. And we don't do very well at all. In fact, we only beat, what is that, 19% for runtime? Yeah, 19% for runtime, 55% for memory, so this is not the best algorithm. One thing you could do, you could make this recursive and use caching. It's basically the same as this DP, so I don't know if that would save you anything. You could try using a stack and using some type of caching. Maybe that would help. What else could we do to make this faster? Because this should be pretty good. We could do this. Well, sometimes these comparisons like this less than. Let's switch this up. So let's just make this, instead of a continue, we'll just check to see if it is within the range. These are ands. I don't know if this will actually help that much. All right, let me get rid of this continue. So now we're just checking if it is within the range, and then we'll do this only if it's in the range. All right, let's see if that helps. Still works. Let's see if it saves us any time. It does save us, but we're still pretty bad on this chart here. So let's see. So that gets us to 27% for runtime and 62% for memory. So that's a little bit better. Oh man, what else could we be doing here? Well, this sum might not be the most efficient. Maybe we could write our own summing, but I don't know. Yeah, I'm not seeing a lot that we could do. Let's see what other people have done. Let's check them out. Let's see, go back to our submissions. All right, let's see what other people are doing here. And for some reason, the page is unresponsive. Nothing's working. What? Well, I think that might be a good place to end it then. Yep, nothing's working. This is completely unresponsive. So with that, I can't do anything. So yeah, so that's it for me. Hope you enjoyed this. Hope you had fun. Hope you learned something. Hope you can go out and write better code. Better than this for sure, because clearly this isn't very good code.